All right, so let's get through what we're going to have a quiz on before break. What I have here is the activity series, which you will be given. And do keep an eye on these. These are some areas here. Replace hydrogen from cold water. We should know that this top group, when they get thrown into water, are very reactive. The flame starts happening. In fact, somewhat off cue. Why don't I look that up real quick? But you can imagine that this happens here, that drop sodium in water. It just starts reacting immediately. It's letting off hydrogen gas, and that hydrogen gas actually ignites from all the heat that's released, and it makes sodium hydroxide. So it's taking the H away from water and taking the H away from water and replacing it with hydroxide. All right, so let's put that away from the top. All right, so these will do that. Lithium, potassium, specifically sodium, and these other metals will replace hydrogen from cold water, react in that sort of spontaneous fashion. Whereas down here, where you have silver, platinum, and gold, you have jewelry in these because they are very stable. You've certainly heard of rocks existing in the world where, panning for gold or whatever, nuggets of these metals, and that's because they're not very reactive and they are happy to stay as they are. So these things, if you actually look at the electronegativities, these have very low electronegativities. They prefer to lose electrons, become ions, and be in compounds. You're looking at alkaline metals, alkaline earth metals on the top. Down here, things tend to keep electrons, high electronegativity relative for metals. If you look at the chart, they're stable as is, and they will stay uncharged, neutral, as they are. So predicting the products of a single replacement reaction using this. So if you have calcium fluoride, so calcium is here in the top group, and zinc is here, which one prefers to be in a compound of those two? Calcium is higher up, it's more active, it prefers to lose its electrons, be an ion based on its electronegativity, it prefers to be in a compound. So that would react. Whereas zinc, because it's a little lower, would not be as reactive. So this would have no reaction because calcium's already in the compound, zinc is not. So zinc would not have such a propensity to knock off the calcium. Silver nitrate and magnesium. So now silver's down here. Magnesium is up here. So magnesium would rather react, would rather be in the compound. Silver prefers to be on its own. So in this case, there would be a reaction. The magnesium would pick up the nitrate and the silver would be off on its own. So that would be, I'm going to try that. So that would be MgNO3 2 is what I'm going to do. So that's what would happen. That would go into the compound. Look at that. Gorgeous. Haven't done that since I was a kindergartner. And that would be 2. And then you're going to have the silver grow on, start coming out of solution if you had a reaction like that. So there you go. Nicely done, says I. All right. So we'll skip that. And cobalt plus water. So that's, again, you're just looking at cobalt is here. The ones that are reactive to water are up here. So that's not going to do anything. And then I'm going to streak across there. Copper, sulfuric acid. So copper is somewhere. Oh, no, it's low, actually. Yeah, here it is. So here's copper. And sulfuric acid is something that would have H as a metal, acting as a metal. Acids would act as a metal. So on the quiz tomorrow, you would see actually just Cu and H2SO4. and you would see that the H is the metal-like thing in the compound H2SO4. And so that having a um, having a higher propensity to be a in a compound would stay in the compound, and copper would not do anything in that regard. So aluminum foil and acid. So here's aluminum here, and acids again would be with H. So since that's higher up, it would replace the hydrogen in an acid. And as a result, if you've ever seen lasagna with tin foil, aluminum foil on it, this phenomenon will happen where it reacts with the acids from the lasagna and starts making aluminum salts. All right, so dissolving salts in a compound. I wonder if that's going to work. Maybe it is. All right, so we have seen that when
Sodium chloride crystals are
get rid of that. So these are the chloride ions, the big ones. Sodium are the smaller white ones. And water will be able to break this apart using its hydrogen bonding special characteristic, where the oxygen is negative and the hydrogens are positive. This hydrogen has a hydrogen bond with water, so it's attracted to the negative chloride ion and will dissolve it and take it away. Whereas this positive sodium ion will attract the negative aspects of water, these negative oxygen sides, to take those away. So that is what happens when you dissolve compounds. And the question is, will certain compounds stay dissolved, or will they be too forced together to come apart? And this chart will tell you what's what. So soluble means dissolving. It means aqueous. These are all aqueous up here. And insoluble means that they will remain a solid. So when we're doing double replacement reactions, the question will be, when you switch your metals, so calcium will switch here, in this case with ammonium, will the resulting things be aqueous or solid? If there's any solid from the result of mixing, then we say a reaction occurred. If they won't precipitate out as a solid, then we say everything's aqueous. It was aqueous, it's still aqueous, everything's just floating around. So calcium going to sulfate will be, sulfates are soluble. They will remain aqueous except for strontium, barium, so not calcium. So that would be soluble. Ammonium going with nitrates, all nitrates up here. Here we are. All nitrates, no exceptions, are soluble. So this would be no reaction because everything would be soluble after changing over. However, here with strontium nitrate, so same anions, different cations. So strontium nitrate and iron sulfate would yield strontium sulfate, SrSO4, and iron nitrate. Not the prettiest thing. Fe, oops, Fe, NO32. All right, so the point here being that iron nitrate would be soluble. All nitrates are soluble, but the SrSO4, soluble SO4 except for when it has strontium, barium, mercury, lead. So this is a strontium one. So this would actually form a solid, and that would be a reaction that occurs for that double displacement. So for double displacement, you're always just going to switch your metals. So in this case, sodium is going to get in where the barium is, and sodium nitrate, if you look at that chart, is soluble. Barium sulfate, let's see if that is, I can't recall. Barium sulfate is not. So that would be the salt that drives the reaction. Remember, we talked about driving forces of reactions. Creation of a solid is one of them. Potassium acetate soluble. Silver acetate is soluble. All nitrates, all acetates are soluble. So in that case, no reaction would occur right here. Acetates, nitrates, always soluble. No exceptions. So that's what we would do in the second part. You would have an equation like this. You would switch your metals, potassium for lead, and see if the resulting compounds were soluble. So this would be lead iodide and potassium